Section 1 Introduction. In this paper, we tackle a complex issue in the realm of online shopping, the visualization of how clothes might look on a person using virtual apparel try-on. The challenge arises when we need to adjust the clothing item to fit various body shapes and poses, without distorting its pattern or texture. It gets even more complex when there's a need to create or flatten wrinkles according to changes in body shape or occlusions. Previous methods have tackled this problem by estimating pixel displacements, such as optical flow, followed by pixel warping and blending with the target person. However, this sequential approach often creates artifacts, as it is difficult to accurately model occluded parts and shape deformations using pixel displacements. It's also tough to remove these artifacts at the blending stage, even with a powerful generative model. An alternate solution proposed by TryOnDiffusion used a conditional style GON2 network to warp without estimating displacements. This technique was beneficial but often lost details, especially with highly patterned garments, due to the low representation power of the latent space. In our research, we present TryOnDiffusion. This system can handle significant occlusions, pose changes, and body shape changes, while preserving garment details at a high resolution of 1024 by 1024 pixels. TryOnDiffusion uses two images as input, one of the target person and one of the garment worn by another person. The output is a synthesized image of the target person wearing the garment. The system has been trained on 4 million image pairs, with each pair featuring the same person in the same garment but in different poses. Our novel architecture, the Parallel-UNet, forms the basis of TryOnDiffusion. It consists of two sub-UNets that communicate through cross-attentions. We leverage two key design elements, implicit warping and the combination of warping and blending in a single pass. The implicit warping between the target person and the source garment is achieved via cross-attention over their features at multiple pyramid levels. This enables long-range correspondence, which is particularly effective under heavy occlusion and extreme pose differences. Also, using the same network for both warping and blending allows these processes to exchange information at the feature level rather than at the color pixel level. This proves crucial in achieving a satisfactory perceptual loss and style loss. To create high-quality results at a resolution of 1024 by 1024 pixels, we take inspiration from Imagine and construct cascaded diffusion models. Specifically, the Parallel-UNet-based diffusion is used for resolutions of 128 by 128 pixels and 256 by 256 pixels. The result at a resolution of 256 by 256 pixels is then fed into a super-resolution diffusion network to generate the final image at a resolution of 1024 by 1024 pixels. In summary, our work brings two key contributions. Firstly, we have achieved try-on synthesis at a resolution of 1024 by 1024 pixels for a wide range of complex body poses and diverse body shapes, while preserving garment details such as patterns, text, labels, etc. Secondly, we have developed a novel architecture, Parallel-UNet, which can warp garments implicitly with cross-attention, and can accomplish warping and blending in a single network pass. We evaluated TryOnDiffusion both quantitatively and qualitatively, comparing it with recent state-of-the-art methods, and conducted a comprehensive user study. This user study involved 15 non-expert users who ranked over 2,000 distinct random samples. The study indicated that our results were chosen as the best 92.72% of the time when compared with 3 other recent state-of-the-art methods. Section Summary. The paper discusses the challenges of virtual apparel try-on and presents TryOnDiffusion, a method that can handle large occlusions, pose changes, and body shape changes while preserving garment details at 1024 by 1024 resolution. The method is based on a novel architecture called Parallel-UNet, which can warp the garment implicitly with cross-attention and perform warping and blending in a single network pass. The method was evaluated quantitatively and qualitatively, and a user study showed that TryOnDiffusion outperformed 3 recent state-of-the-art methods 92.72% of the time. Section 2 Related Work. In this section, we discuss existing work related to our research. This includes methods used in image-based virtual try-on and advancements in diffusion models. Starting with image-based virtual try-on methods, these techniques allow for a digital representation of how a certain clothing item, the source garment, might look on a target person, using just a pair of images. The approach typically involves 2 parts, a warping model and a blending model. The influential work, Viton, introduced a step-by-step method directed by thin plate spline or TPS warping of the source garments. In contrast, ClothFlow utilizes a neural network to estimate flow fields rather than relying on TPS, providing superior garment warping. Viton HD, an enhancement to Viton, uses an alignment-aware generator to heighten the resolution of the TryOn from approximately 256 by 192 to roughly 1024 by 768. Our Viton builds on Viton HD, predicting segmentation and flow at the same time. SDAFN anticipates multiple flow fields for both the garment and person and blends these warp features using deformable attention to boost the quality. Nevertheless, these methods encounter issues due to the misalignment caused by explicit flow estimation and warping. TryOnGAN addresses this by training a pose-informed style GAN2 on mismatched fashion images and fine-tuning in the latent space for the TryOn effect. However, this approach can often result in losing minute details of the garment that are poorly represented in the latent space, particularly noticeable with garments that have patterns, pockets, or unique sleeve designs. We suggest a fresh architecture that accomplishes implicit warping, without flow calculation, and blending in a single network process. Our experiments indicate that this method can preserve garment details even in challenging conditions of heavy occlusions and diverse body shapes and poses. Now let's turn to diffusion models. These models have recently become the most potent class of generative models. Contrary to GANs, diffusion models demonstrate superior training stability and mode coverage, achieving leading-edge results in various image generation tasks like super resolution, colorization, novel view synthesis, and text-to-image generation. However, even top-tier diffusion models employ a conventional UNet architecture with channel-wise concatenation for image conditioning. This works well for image-to-image translation problems where input and output pixels align perfectly, such as in super resolution, inpainting, and colorization. Yet, it isn't directly applicable to our task since TryOn involves highly nonlinear transformations like garment warping. To overcome this hurdle, we suggest a Parallel-UNet architecture tailored for TryOn, where the garment is implicitly warped via cross-attentions. Section Summary. Image-based virtual TryOn methods generate the look of a target person wearing a source garment by decomposing the task into warping and blending models. Various methods have been proposed, including Viton, Clothflow, Viton HD, Our Viton, SDAFN, and TryOnGAN, but they still suffer from misalignment. The authors propose a novel architecture that performs implicit warping and blending in a single network pass, preserving garment details even under heavy occlusions and various body poses and shapes. Additionally, diffusion models have emerged as powerful generative models, but traditional UNet architecture with channel-wise concatenation is not directly applicable to TryOn. Therefore, the authors propose a Parallel-UNet architecture tailored to TryOn, where the garment is warped implicitly via cross-attentions. Section 3 Method. Our method focuses on a virtual TryOn system. To understand the process, consider an image of a person, let's call it person image, and another image of a different person wearing a particular garment, which we'll call garment image. Our system generates a new image, the TryOn result, which shows the first person wearing the garment from the second image. Our system's learning process utilizes pairs of images, where the person and garment are the same, but the person is posed differently. However, when it comes to actual usage or inference, the person image and garment image represent two different people, in different clothes, and in different poses. Let's talk about how we preprocess these images. Firstly, we use existing methods to generate a human parsing map, essentially a detailed segmentation of the person and garment images, and 2D pose keypoints, which identify important elements of body posture for both images. For the garment image, we specifically isolate the garment using the parsing map. For the person image, we create a clothing-agnostic image that keeps the identity of the person but removes the existing clothes. This is a tricky step because there can be scenarios where the original clothing might still be discernible in challenging poses or with loose garments. To avoid this, we aggressively remove all the information related to the garment. We do this by masking out the entire bounding box area of the person in the foreground, and then paste only the head, hands, and lower body part onto it, thus eliminating any trace of the original garment. The body parts which are not part of the garment are extracted using the human parsing map and the pose keypoints. To ensure consistency in the inputs to our system, we also adjust the pose keypoints to fit into a scale between 0 and 1. The inputs for our TryOn system include the clothing-agnostic image of the person, the pose keypoints of the person, the isolated garment image, and the pose keypoints of the garment. Moving on, let's give you a brief overview of diffusion models, which are central to our method. Diffusion models are generative models that learn to represent a target distribution through an iterative denoising process. Essentially, they have a forward process that slowly degrades the data sample into Gaussian noise and a learnable reverse process that converts this noise back into the data sample. One of the fascinating properties of diffusion models is their ability to be conditioned on a variety of signals like class labels, texts, or images. This conditioning allows the model to generate data samples that correspond to these signals. In mathematical terms, a conditional diffusion model can be trained with a weighted denoising score matching objective. This is done by comparing the cleaned, noisy data sample generated by the model to the original data sample. The process introduces some level of noise that affects the final quality of the sample. When we want to generate new data samples during the inference stage, we can create them from Gaussian noise using specific sampling techniques. This is essentially the reverse of the corruption process mentioned earlier. Section summary. The method for virtual try-on involves generating a try-on result of a person wearing a different garment. The approach is trained on paired data of the same person wearing the same garment in different poses, but during inference, different people wearing different garments in different poses are used. Preprocessing involves predicting human parsing maps and 2D pose keypoints for both person and garment images, and diffusion models are used to learn the target distribution through an iterative denoising process. Section 3.1 Cascaded diffusion models for try-on. Our cascaded diffusion models are made up of one primary diffusion model and two additional super-resolution diffusion models. These models are created to carry out a process we call try-on. The primary diffusion model is designed with a structure known as Parallel-UNet and it's configured with dimensions of 128 by 128. Its function is to generate a preliminary try-on result, referred to as I_text tr_128, based on certain inputs, which we will call C_text try-on. However, two of the inputs, I_a and I_c, can sometimes contain inaccuracies due to the imperfect process of human parsing and pose estimations. As a solution to this, we introduce a technique called noise conditioning augmentation, where random Gaussian noise is added to I_a and I_c before any further processing. The degree of noise we add is also considered as part of the conditional inputs. Moving to the next step, we have a super-resolution diffusion model that's designed with a size of 256 by 256. This model is configured as a larger Parallel-UNet. The job of this model is to produce a more refined try-on result, named I_text tr_256. This is achieved by using both the initial 128 by 128 try-on result and the try-on inputs at a resolution of 256 by 256. During the training phase, the model uses a reduced version of the ground truth to generate the 128 by 128 try-on result. But during actual tests, it uses the output from the primary diffusion model. In this stage 2, we use the noise conditioning augmentation method for all the inputs, including I_text tr_128, I_a, and I_c. Finally, we have another super-resolution diffusion model that's designed with a size of 1024 by 1024. This one is configured using a structure called efficient UNet introduced by Imagine. This model's role is to serve as a pure super-resolution model without any try-on conditioning. For its training, we use random 256 by 256 samples from a 1024 by 1024 ground truth image, and inputs are 64 by 64 images, which are simply reduced versions of the samples. When the model is in operation, it takes the 256 by 256 try-on result from the previous model and generates a final try-on result at a resolution of 1024 by 1024. To support this configuration, we've made the network fully convolutional by removing all attention layers. Similar to the other models, we also apply the noise conditioning augmentation technique to the input image. Section summary. The cascaded diffusion models for try-on consist of a base diffusion model and two super-resolution diffusion models. The base diffusion model predicts the 128 by 128 try-on result, while the super-resolution models generate the 256 by 256 and 1024 by 1024 try-on results by conditioning on the previous result and try-on conditional inputs. Noise conditioning augmentation is applied to all conditional input images during training and inference. Section 3.2 Parallel-UNet. Section 3.2 is about a specific type of neural network known as the Parallel-UNet. This network comes in two sizes, one with a resolution of 128 by 128 and the other with 256 by 256. The smaller network can be described using a formula that involves several variables. The variable t represents the diffusion time step, while z_t stands for the noisy image that deviates from the original or ground truth image at time step t. The variables c_tryon and t_na represent TryOn conditional inputs and a set of noise augmentation levels for different conditional images respectively. The variable, epsilon_t, refers to predicted noise that can recover the original image from the noisy one. The larger 256 by 256 Parallel-UNet uses the TryOn result, denoted as I_TR128 feet, as input, as well as the TryOn conditional inputs at a resolution of 256 by 256. There are two critical design elements in the Parallel-UNet. 1. Implicit warping. The challenge of introducing implicit warping in the neural network can be addressed by employing a cross-attention mechanism between our streams of information. This mechanism is based on the scaled dot product attention, where Q, K, and V represent stacked vectors of query, key, and value respectively. The dot product gives the similarity between the target person and the source garment, offering a learnable way to represent correspondence for the TryOn task. 2. Combining warp and blend in a single pass. Unlike previous methods that first adapt the garment to the target body and then blend it with the target person, we integrate these two operations into a single pass. We accomplish this by using two UNets that manage the garment and the person independently. The person UNet takes the clothing agnostic RGB and the noisy image as input, while the garment UNet takes the segmented garment image as input. The garment features are combined with the target image via the cross-attention mechanisms described above. To save on model parameters, we halt the garment UNet after the 32 by 32 upsampling block. The person and garment poses are crucial for guiding the warp and blend process. These are initially fed into linear layers to compute pose embeddings separately. These embeddings are then integrated into the person UNet through the attention mechanism. Additionally, pose embeddings are reduced along the keypoints dimension using clip-style 1D attention pooling, and combined with the positional encoding of the diffusion timestep and noise augmentation levels. The resulting 1D embedding is used to modulate features for both UNets across all scales. Section summary. The Parallel-UNet architecture consists of a 128 by 128 and a 256 by 256 network that use cross-attention to achieve implicit warping between the noisy image and the segmented garment. The garment and person UNets are combined into a single pass by concatenating the clothing-agnostic RGB image and the noisy image, and fusing the garment features to the target image via cross-attentions. Pose embeddings are used to guide the warp and blend process and modulate features for both UNets using film. Section 4 Experiments. In our experiments, we used a dataset composed of 4 million pairs of images. Each pair included two photos of the same person, wearing the same clothes, but in different positions. For testing, we utilized 6,000 pairs of images that were not part of the training set. These test images depicted different individuals wearing different clothes and posing differently. All images were adjusted to be 1024 by 1024 pixels in size, based on the detected human poses within them. Our dataset was diverse, containing men and women with different body shapes, skin tones, and a wide range of clothing styles and patterns. We also used the Viton HD dataset in our experiments. To implement our models, we trained them in batches of 256 for 500,000 iterations using the Atom optimizer. The learning rate was gradually increased from 0 to 0.0001 in the first 10,000 iterations and remained constant afterward. The model training was conducted without classifier supervision and incorporated a technique called conditioning dropout. Test results were generated in a structured manner using 3 versions of our model, each focusing on different aspects of image detail and complexity. We used different sampling steps for these stages and set the guidance weight to 2 in all cases. We introduced random levels of noise during training, and at testing, these were set to constant values determined by grid search. We compared our method with 3 other techniques: TryOnGAN, SDAFN, and our Viton. To ensure fairness, we retrained these methods on our 4 million sample dataset. We found that without this retraining, their performance was inferior. Notably, the original versions of SDAFN and our Viton required a lay-flat garment as an input, which was not suitable for our study. The results from these techniques were showcased in their native resolutions: SDAFNs at 256 by 256 pixels, TryOnGANs at 512 by 512 pixels, and our Viton at 1024 by 1024 pixels. Quantitatively, we measured performance using 2 metrics: the Frechet inception distance, FID, and kernel inception distance, KID. Since our test dataset was not paired, these metrics were ideal for our evaluation. The performance of our method was significantly better on both test datasets. To validate our results, we conducted 2 user studies. In the first one, we randomly selected 2,804 pairs of images from the 6,000 image test set, ran all 4 methods on these pairs, and asked non-expert reviewers to rate the results. Our method was chosen as the best in over 92% of cases. In the second study, which we labeled challenging, we repeated this process with 2,000 pairs of images that involved more complex poses. Our method was selected as the best in almost 96% of cases. We also conducted a qualitative comparison by visually comparing all methods on 2 test datasets. We observed that TryOnGAN struggled to maintain the texture pattern of the garments, while SDAFN and Our-Viton introduced distortions in the TryOn results. Our approach, however, preserved the fine details of the original garment and blended it seamlessly with the person, even in challenging poses or with complex materials. We performed 2 ablation studies as well. The first one compared the use of cross-attention versus direct concatenation for implicit warping. We found that cross-attention preserved garment details better during significant body pose and shape changes. The second ablation study contrasted the results of combining warp and blend tasks versus sequencing the two. Our results indicated that the latter approach could cause artifacts near the garment boundary, while combining the 2 tasks within a single network resulted in a better blend of the target person and the source garment. Our method had some limitations. It was susceptible to garment leaking artifacts due to errors in segmentation maps and pose estimations. Moreover, using clothing-agnostic RGB to represent identity was not perfect, as it sometimes only preserved part of the identity. Furthermore, our training and testing datasets mostly included images with uniform backgrounds, making it unclear how our method would perform with more complex backgrounds. Also, our focus was on upper body clothing, so we haven't tested the method with full body try-on scenarios. In the end, we demonstrated the results of our TryOnDiffusion method on various people and garments. Additional results are available in the supplementary material. Section summary. The authors collected a paired training dataset of 4 million samples, each consisting of 2 images of the same person wearing the same garment in different poses. For testing, they collected 6,000 unpaired samples of different people wearing different garments under different poses. The authors trained their models with conditioning dropout and compared their approach to 3 other methods, achieving significantly better performance in both quantitative and qualitative evaluations. Section 5 Summary and Future Work. In this section, we're summarizing our work and looking at potential avenues for future exploration. We've developed a method that can generate images of people trying on specific clothing, using just a photo of the person and an image of the garment. The quality of the resulting images is significantly superior to anything currently available, with an excellent match to different body shapes and poses and a high fidelity to the original garment. The key to our success has been the innovative architecture we've named Parallel-UNet. In this system, 2 separate UNets, a type of neural network used for image processing, are trained in tandem, with one network transmitting information to the other through cross-attention. Mechanisms. This unique arrangement has been instrumental in generating results that outshine the competition. But our vision extends beyond just virtual try-ons. We foresee this architecture making a significant impact on the broader field of image editing, which we're eager to investigate further. And, taking this a step further, we believe it's possible to adapt this architecture to video applications, a challenge we're excited to take on in the future. So, while we're proud of what we've accomplished here, we're even more excited about the potential applications still to come. Section summary. The presented method for synthesizing try-on using images of a person and a garment outperforms state-of-the-art techniques in both warp quality and garment preservation. The Parallel-UNet architecture, which uses 2 UNets trained in parallel with cross-attentions, is responsible for the state-of-the-art results and has potential for general image editing and video applications. Future work will explore these possibilities.